Okay, hello, welcome back. So in the previous videos, we started looking at curvilinear motion and we saw how we can describe this motion, positions, velocities, and acceleration in a rectangular frame. Rectangular frame had the x, y, and z components, also known as the Cartesian components. It was a very useful frame to work with motions that we know, either velocities, positions, accelerations, similar to ideas similar to those along the three components, three x and y components. But that is not the only way we can describe a motion. Consider a scenario, for instance, a roller coaster. Roller coaster is probably the best example. Ooh, that's not a good roller coaster. Something like this. You're here, you go up. Oh, that's a very dangerous roller coaster. Anyways, the path is always the path you take, the cart take, is always fully constrained to remain close to the track. So we have full knowledge of the path, although it's not a straight line path as in rectilinear motion, but nonetheless we have some knowledge about the path the particle takes. So in this condition, we can try to use this pre-existing information to help us define the kinematics of this particle better. So one thing to remember what we mean by changing a frame or a frame in general. So let's consider a particle that has some velocity. It is a velocity in a space, and the particle is moving. In the past, with rectangular frame, we chose to have some x and y frame perpendicular to each other and often perpendicular to the page or to the world. And we describe this velocity with components along the vx and component along the y vy. But velocity of the particle is not, it's a bit stubborn. It doesn't care how you're looking at it. If I draw the particle again with its ever-existent velocity, feel free to tilt your neck and look at this in a different way. Now have some perpendicular axes that one of them is aligned. Let's call it x prime and y prime. Now the same velocity that exists in the world has different components. The x prime component, vx prime, is actually has the same size of the velocity, and vy prime is 0. So the components changes, but the vector remains the same. That's what we mean by looking at the velocities or describing the motion in a different frame. The components essentially change. So that's what we want to do. We want to find a new frame that uses the information about the path, and that hopefully helps us simplify the problem. So how do we do that? For simplicity, let me look at a simpler path. What I can do, I can consider the particle at different points along this path, as many as you want, and define my coordinate frames that I'm looking at to be one of them always tangent to the path and another one normal to the path. I can do this at any other point, any point I want. So at any point, I can always define a coordinate frame with two axes, one perpendicular or normal to the path, another one tangent to the path. This tangential and normal components are what we call usually TN, or tangential normal frame. And note that it is the direction of this set of axes always change as the motion, as the path, as the particle moves through the path. So it's no longer a fixed frame, it is a changing frame. So Tn changes as particle moves. Oh no, that's too far out. Here. Okay, now let's see how we can formally define and use this. The first step is, now that we have a changing frame, how do we define this uniquely at any time? So frame definition. Again, we have a path. Let me draw it here. A particle on it. The first thing we need to find is what is its origin. What we can do, we can always define or we want to do it actually, not that we can, we want to. We define it always at the location of the particle. So the origin of the frame is at particles location. So this is the origin. We then need to define the two directions of the two axes. We define the t-axis, or tangential one, to be tangential to the path. So it is along this tangent, but we have two choices, either forward or backward. And we define forward by considering a reference point S, or some reference points, and the distance along that path from the reference. And we take our tangential to be in the direction of increasing S. In the direction of increasing S. S here we call it path coordinate. Coordinate. Because it tells us how far into the path we are. And finally, we can define the n-axis, the normal axis. We define it perpendicular to t-axis. But note that in this case, we have infinite number of possibilities. Although I have drawn the curve on the 2D surface of this page, you can think of a path to be general 3D motion, such as a spring, a coil spring, or a helix that moves through this space. The tangent is uniquely defined, but not necessarily normal to it, because it can be anywhere on the plane that is tangent or normal to this tangent. So it can be any of these remain normal to tangential axis. Which one is it? Let me delete this. We take the one that points toward no T. Another GOW toward center of the curve. So at any time, if you consider the curve to be a piece of a circle, that circle, that arc, has a center, and our normal is the one that points toward that center of the curve. So with this, we have fully defined our t and n unit vectors or axes. And there is a third one we can define, because we are often dealing with three-dimensional space. We can define a b-axis. It's a binormal axis, so it is perpendicular to both t and n axes. And in this case, I'm not going to draw it because it looks very messy. Maybe I can try it. Let's see. Let's call this the b. B is perpendicular to both this and that. Okay, that's how we define the frame. Now, maybe half of our work is done. The rest is defining positions, velocities, and accelerations using these three unit vectors. The same way we had defined position, velocity, acceleration using ijk. Now we want to define them using t, n, and b. All right, so let's begin, as always, by position. Position is actually a little different with this curve, because we normally don't define the position. If you are using normal tangential frame, we don't define position using any of these. We can do the same thing as we had done with rectilinear motion. Because path is known, it is a lot more convenient to use the scalar path coordinate s along the path to define the position. If we know the path and we know in which direction and how far along that path we are, we can fully define without any ambiguity where the particle is. You would wonder, if this is how we define it and we don't use the normal tangential components, then why did we even define it? The usefulness comes when we define velocity. Velocity, as you always should remember, and you remember, v always tangent to the path. And that is the biggest purpose we define normal tangential, because velocity, now by definition, is our speed, normal velocity, in the tangential direction. I use u sub t to define, this is the unit vector along the tangential direction. And you can see immediately the purpose of why we have chosen this. Because immediately velocity is extremely well defined, compact form as the speed in the tangential direction. I think I'm good for now. One other thing, always remember, norm of v is the speed. So whenever you see the speed and you know the path of the curve, you can immediately use normal tangential frame to define the velocity vector. So I think I'll stop here. In the next video, we look at the acceleration definition in normal tangential and a few remarks, and we should be done.